Okay, so do I have everybody's homework? All right, just bring it across the street. I get that. PhD student forgetting his homework. Should bring you in front of the class and whip you. Punishment. All right, so before we start, I want the two things, the things I want you guys to do this weekend in addition to homework assignments. What I want from the undergrads, I want you guys to find a partner to work with on the laboratory assignments and send me that email by Monday. So you're all here, so don't know each other. I'll introduce you guys. Grad students, I want you to come on IEEE Explore, and I want you to find an IEEE Transactions Journal paper, not a conference paper. I want it from a Transactions Journal that you are going to select. George has already selected one, so now we're even on forgetting your homework. But, it has to be about low-power digital design, and I prefer it to be about synthesis, some sort of synthesis approach, and it cannot be one of my papers. So that's what I want. I want your proposed paper. You can email me the name of the paper and the citation to me by Monday. And that's going to be the one that you're going to be presenting on. So ideally, it should be something that you're interested in, or and it has to be related to the course in some way. All right, so now that I've got that out of the way, we're going to start back up here. So last lecture, we went over some of the fundamental physics that you need to understand how a MOSFET works, and then how you actually tie them together to make logic. Throughout the rest of the course, we're going to be talking about transistor sizing, resistivity, electron punch through, but we kind of got the general idea. But before we start, what I want you to understand is how the logic is actually working. So we went over some fundamental ideas. We created a 2-input AND gate and a 2-input NOR gate. And we did an AND gate, we have to add an inverter. We have this whole idea of these pull-up and pull-down networks. Where either we want to pull the pull-up network, and you want to pull it up to supply voltage, or pull it down, meaning you want to pull it down to ground. And then, as we get into more detail, we'll understand the concepts of noise margins and how that impacts threshold voltages and switching. But for now, what I want you to understand is I want to give you a logic problem or something similar. And then you can actually create the circuit. And then we're going to study something about stick diagrams. Now, a lot of what we're studying in this course is about synthesis, meaning that there's different levels of abstraction. All of you have had me for 385. I'm going to be going over that Gauss-Key-Kahn chart again. It's very important, especially in the context of this course. You have to understand the levels of the cells. We've gone from the physical layer all the way up to transistors. Now we're at the transistor layer, right? So now we're understanding how we put transistors together to make circuits. So in this particular problem, what I'm giving you is the function is equal to the negation of D or A and the quantity B or C. So in this particular case, what we want to do is we want to start with the pull-up network. If this actually decides it wants to cooperate and do the touch screen stuff. It is, there we go. All right, so for the pull-up network, so what type of transistors in pull-up networks? PMOS. And what type of transistors are in pull-down networks? NMOS, right? So for the pull-down, so for the pull-up network, are in parallel or series? For the pull-up network, are ANDs, meaning I had NAND of A and B, right? So were those transistors for the ANDs, are they in parallel or series? Series. And OR gates, so for the OR, the transistors are in. So for the pull down, that means that ANDs are in parallel and ORs are in some. Okay. So now we have a number of these different values, right? So we start out here, and then I might have to use the mouse on this one. So here, we actually did this problem, but I want to kind of review it. So, or for the pull-down network, it's going to be in parallel. So you start with ground, right? So you either draw ground like this, or you can do a little thing like they've done here. But you start out, and then D is by itself, so you can have the NAND, and it's going to go up here to the output. Now, this means that the ANDs here, A and B or C, right? So you can also do it like this. You go to A, and then, I'm sorry, this is, that's, it's actually going to work. It's not cooperating today, nor is this. So these all go to the output, just like so. And so what does this logic mean? All right, so if D is a logic 1, that means you're going to push the holes down, and you're going to push the hole, you're going to allow this to go through, right? So you put his 1 on here, think of it as the inverse. So the same thing, that you need either A and B or A and C in order to get the flow to go through, right? So when you're doing it in the opposite direction, we have this pull-up network. B or C and A and D is ORed, so they're in series. So in this case, what this means that in order to get the supply voltage on a pull up to 1, you either have A is 0 and D are 0, or you have to have B and C are 0 and D is 0. Does this make sense? And then you put the circuits together in the pull-up, pull-down combination, which is why they're complement, which is what the C in CMOS stands for. You have your final solution. Now, as I said before, I used to do a more complicated De Morgan's law, which basically is a mathematical way of coming up with the exact same parallel series trick that we just came up with. And on an exam, I'll ask you a question that begins with a negation, like so. Now, what would happen if I gave this to you and there was no negation? Yep, just negate and put an inverter on the end. Does anybody have any questions about this? No? All right. Okay, so in order to further understand how transistors are put together, in order to understand how these stick diagrams work, we want to go into the different aspects of the fundamental masks using CMOS. And what I've used by mask is that we actually have these different layers that are put together. And what I can actually do, I spelled process correctly. I'll do CMOS lithography because that'll come up with a. That's not what I searched for at all. Thanks. I used to have a link in there that I could show you. So you suck at writing, you can use Grammarly.
Company.
So this is a Taiwan Semiconductor Corporation. Actual wafer. So actually we use it's going to go to the silicon wafers. The reason this is important is on any of them, not throw the whole thing away. So what they'll talk about there, at those these metal these are different layers of lithography layers. Silicon. These are great examples. They really drove past this. This whole thing, you see this right here? That's the silicon ingot is huge, and they try to cut thousands and thousands of wafers out of each one. So they heat it up to about 800, 850, 900, 1,000 degrees, and they make it pure silicon. So you see this right here, you see how reflective it is? They're trying to get out all of the impurities to start out. And this is important because, as you know, you want to have these holes in electrons flow through the PMOS and NMOS to create those channels, right? So anything that could potentially absorb an electron or contribute to a hole that is not silicon is an impurity and would actually hurt the ability of the circuit to do so, to conduct. But you'll study. You'll blow up one of those by the end. Those different layers include the N well and the P well and the silicon sublayer. And you have to have them in different ways in the middle. And the critical layer, and we'll get into this, more wires you have in one allows you, as the technology size gets smaller and smaller, you have more wires going through a different level. They'll actually layer it in order to have it washed out so you can move all the energy. There's you took CMOS with me. I talked a lot about how first few made and 1,000 of them are essentially the same cost. This is why, because you can actually put 10,000 chips of the same design into all of these different integrated circuits and have them cut up. And it's just because you have to make one giant silicon tube anyway. So we'll close that out. So that allows you to really reduce cost if you actually design it properly the first time, which is why you have to do all the design for testability, and you have to do all the checks at the end of your process. So the reason I wanted to show you this is because there are 6 types of fundamental masks used in CMOS. So you're already familiar with N diffusion, N plus diffusion, should be N minus. So polysilicon. And you don't worry about the 20 angstroms for now, because we're going to be doing different technology sizes. So what's going on here is that you recall that there's the base of silicon, which is which is not doped at all, and then you have your N well, which you put into the positively doped silicon portion, right? So you have the N well that surrounds the two P diffusions for your PMOS circuits. The N plus diffusions, they just put it straight into the silicon wafer. Polysilicon is what is in between your transistors. So so if you have, that's right, it's not cooperating today for some reason. So remember you have your diffusion regions and you want to create your channel. So you have this thin silicon dioxide layer with a mask here. So you got your transistor. And then to actually connect everything, you're going to use what are known as polysilicon. So that's where you put your gate. Okay, so you use polysilicons and metals to transmit your signals. Now, the way that you actually connect your metal and your polysilicon are what are known as contacts. So contacts, you have polysilicon and the metal, you put the contact together, and it actually allows you to transfer the signal through to the gate, which will then create your channel. Does that make sense? And so the way that this is set out, so this is kind of done in the order of the lithography process that I just showed you. So there's 6 of those, so those are important to know as you move forward. I used to, in CMOS, I went in a lot more detail about the layout design rules. Those are going to change in this particular course because we're actually going through a design process where you may have different sizes, and I don't want to restrict you to the specific layout design rules as of right now. But the one important thing to note is the feature size. The feature size is the distance between the source and the drain. And it's set by the minimum width of the polysilicon. So anytime you hear 22 nanometers, 90 nanometers, 0.13 micron, all these different transistor sizes, that's the feature size. So the feature size is the minimum size that the channel needs to be in order to actually conduct. And if I don't mind me, I'm going to scroll down a little bit. Oh no, I want some news. I have a news article that just says feature size of Intel's 14 nanometer technology-wise. So companies like TSMC or Intel or AMD, as they're starting design elements in new feature sizes, they tend to keep it proprietary. So it would be very hard for us to use Intel's 22 Ivory Bridge feature size, but there are what are known as predictive technology models out there. So you can actually go in here. For example, you could select the type of the latest models. Let me go in here. Okay, so here they have predictive technology models here. So you have 22 nanometers, 16 nanometers. So here, so these PTMs, they have them for high performance and low power applications. So they'll actually, so if we go into 22 nanometer here, this is actually going to have the model for your NMOS circuit as well as your PMOS circuit. So all of the element values that you would actually need to know in order to design a circuit, they have them in there. And these files are known as technology files, meaning it actually describes the actual technology that you're going to simulate in the tool. So here you have the threshold voltage that would be required to change from a logic 0 to a logic 1. And same thing, you have the width of the oxides, TOX, it's oxide thickness. So that's an example. So here I have a comparison between 0.13 micron, and here's the size of that transistor. And over here, you probably, right here, that's the same transistor size at 22 nanometers. And so we can see that it's following our design process is pretty well following Moore's law. And so as you see, they're getting down to 16 and 14 nanometers. And then here's that news article, 14 nanometer revolution, why you should care. And I added the little polysilicon width. So stick diagram. So now we understand that there's different layers, and we understand the physical aspects of it. However, if you're a low-power digital designer and you're using these different tools, you have to be able to design for different technology sizes, which means that we're going to design at a different layer of abstraction. So here, we don't have all of this, the widths of the polysilicon, we don't have the sizes, the requirement of the metals, we don't have the size requirements of the diffusion regions, but we can represent them in this stick diagram. So as you recall, or you may recall from when we were going over, you had your diffusion regions for your NMOS transistor, and then you had a metal here that connected our outputs, and then you had the diffusion regions for the PMOS, and then you had your N-well, right? Remember all that? So that is looking from the side of your inverter. These stick diagrams are looking down on it, because as you do the rest of your synthesis, everything else is looking down. So what's going on here is that if the in another way of looking down on it, so we have our PMOS transistor, and we have our NMOS transistor, and we have our output. And we have some sort of input here, and we have some sort of output, right? So what's going on here is we have supply voltage, we have ground, we have PMOS and NMOS. So our N diffusion region, this is our actual NMOS transistor. So this is our source, and this is our drain. Similarly with the PMOS, which is represented in yellow, this is our source and this is our drain. And so what we're doing is we have this polysilicon, which represents the input, A, and then we have an output Y here. And these X's represent contacts. So we have a contact coming in from a metal, which represents ground, and the contact transfers to the NMOS source, right? So recall from, if you actually go back and look at the diagrams from the patent, you'll actually see how the contact works. And we'll go into that in more detail if you like. Here, then what happens is, if let's say that the input to A is A1. Well, here's what's going to happen. You put the input for 1 there, it goes to the PMOS and NMOS transistor. Pushes the holes down, it attracts the electrons here, this is cut off, and the flow from ground goes to this output. Likewise, when you have 0, it's going to attract the holes, and then here it's going to repel the electrons, then it will flow to be able to create a channel. There. So that's how that works in the stick diagram. And so the stick diagram, the benefit is that you can actually do the layout, the logic using polysilicon, P diffusion, N diffusion, contacts, and metal in order to represent the logic and then have it transfer to whatever technology you're using. So this is technology independent, or technology size independent. Does that make sense? So what I want to do here for the next problem is we're actually going to go over how to make these. Right, so for the pull-up and pull-down networks, basically what you want to do is you want to replicate this, but you want to do it as a map from ground to the output. So in this case, what's going on here is that the map either has to go through A and B, or C and A, or D. See how that works? And it comes out just like this. So you draw the diagram, you draw the pull-up and pull-down networks for the PMOS and NMOS transistors. And then what you do is you actually use this as a map. And what we're going to end up doing is we're going to take this and we're going to actually design the circuit such that we actually have a map that you can flow from this transistor, from ground to this transistor. And likewise, we're going to do the same thing for the pull-up networks. And as I've shown here, and this is, so I say this is example 1.5, so you already know these values here. So I don't like what they did here. So what I would rather you do is you have VDD, and you just do the same drawing. So you have to have C, B, and that goes here, and then A comes this way,
right? And then you're going to have D go to output. So, or we'll call this V out to maintain consistency. But you see how the path works? So what we're going to do is we're actually going to design our circuit, our stick diagram, to reflect this path. So see here, this would be, if this was A here, you want it to flow through A to get to the output. If it had to be A and B, we would put another one here, and then the metal output would be there. Does that make sense? So in this case, we have C and B. So in this case, we could have ground, and we have a contact and diffusion. This would be C, and then we could go through B, right? And then we have another one where it has to go through A, contact. We'll call this A here. And then we have this value D. So the D transistor you actually has to go through D in order to get to the output. Likewise, we'll do the same thing. So I'll show you how the whole process here on the next page. So what you do is you draw your outputs. You figure out what order they need to go through. So here, D, A, B, and C. You want to keep C and B together because, as you will see here, in the pull-up network, you have to go through C and B, and here you have to go through C or B. So I'm going to show you how to actually use metal to make a decision here. So first thing you want to do every time is you draw out your supply voltage, your ground, your P active, your N active, and V out. So you'll be allowed to bring colored pencils into the exam for that. And so the first thing you want to do is, in this case, I've selected Pulldown Network, but you can do either order. So here's how the map works. So it has to go through the D transistor, right? So one path that just goes from ground to the D transistor. So in this case, this here goes from ground through D. I should be able to zoom in here if everything's cooperating. Good enough, right? So here, I'll reiterate, ground through D. So it's going from ground, goes through here, goes through a contact, goes from the source to the drain on the D transistor, and goes to V out. You see? And it has to do one of two things. So this is how you do a decision. So what happens is it can either go from ground to B. So what happens is it goes from the source to the drain of the B transistor, and then we use a metal to go around the C transistor and go through A. You see that? So same thing. You go through B, goes around C, and goes through A. Or it goes from ground through the C transistor and then through the A transistor to the output. Does that make sense? Does anyone have any questions on this? So for pull up, what we can do is it has to go through the D transistor to start, right? So at one point it has to go through the D transistor. So the easiest way to do this is just, first thing I'm going to do is I'm going to go through the D transistor. This is for PMOS, and this is for NMOS. So what we're talking about here is we have the active regions, basically the diffusion regions that represent the source of the drain. And so what you would have is you would have a P-active region for all your PMOS transistors in the cell, and an N-active region for all your NMOS. So when we break this down, we actually get into the actual process, especially when we're using Virtuoso. You'll be able to see how these all tie together. But ideally, we want to have them there so that we can keep them close to your ground or your VDD. So in this case, and let me scroll up because I think I wanted to address one thing. So here they have this drawing. We have to D is on the last thing on the output. Remember how I told you can actually switch these? In this instance, just you can see that it always has to go through D, right? So in an instance where it always has to go through D, sometimes it's just easier to put D first. And in this case, we have. And so we have our pull-down network, and then we add our pull-up network. So the first thing you do, we have the supply voltage goes through the D transistor. Now, it can make one of two choices. We choose if D and A for the pull-up are both 0, then we've satisfied this. So this allows us to go straight just through the A transistor from the source. So we hook up the drain of the D transistor with the source of the A transistor, and it just goes through A to the output. See how that works? Likewise, if we go through D, we need to circumvent the A transistor somehow. So here, the way we do it, and since C and B are together, and we want this to go to the output, the way we do this is we hook, and you can do this either B or C or B, it's in which direction, as long as it matches this order down here as well. What you do is you go circumvent the A transistor with a metal, and then we go through the B transistor and the C transistor, and then go to the output. So in that way, now that we understand the physics of everything, I want to show you a stick diagram, and I want you to tell me what's wrong with it. And that's the end of the previous question. I want you to do the path diagrams and the stick diagrams for 1.5. So what's wrong with this stick diagram? Nobody who's answered who's taken syllabus last year or answered.
Maybe that part of the right.
Correct me.
Down.
Here? Yeah. What's wrong with it? Why is it wrong?
I'm assuming they're not supposed to cross like that, maybe, or something.
So what's the term for when it crosses?
B starts with an S.
Short. We have a short. So what happens here is, just like to represent the path. What ends up happening is ground. So it doesn't matter whether it goes to B or C, right? So I can go to B, but if I go to here, if it goes here, it'll automatically cross C, right? Likewise, if I have B, remember it has to be B or C, so normally we would have it like this, so we're going to get around. But if we go, you can actually have the source and the drain go like that, or it's shorted out, so it'll go this way. Or it can just go, and here's the key thing, it can just go this way. So that messes up the logic. So we've shorted it out. So we ended up shorting out is we just said this doesn't exist, and we just go to A on the output. And so putting this all together, so I'm going to go through the whole process with the logic question of actually putting together the pull-up and pull-down networks and then drawing the stick diagram. So design the CMOS transistor so it's A and B or D in the quantity C or E. And so this is the method I'm teaching you this semester. Method 1, no De Morgan. So what's ended up happening is for the pull-down network, ANDs are in series and ORs are in parallel. So we have A and B, and then D and C or E. Does that make sense? Let me zoom in here a little bit so you all can see. All right, so there's the pull-down network here. like that. And then the pull-up network, the ands are in parallel and the ors are in series, which means we have A and B here for PMOS, and then D is in parallel because it's and then C and E are in series with OR. So a properly designed circuit just ties them both together. So then we'll skip over this part, which is basically just doing the De Morgan to come up with the same thing. And so here are our path diagrams. So our path diagrams, so go for the pull-up network. So it can be A and B. You can go from A or B. Or I'm sorry, since they're in parallel, A and B, they have to come to the same spot. It has to go through one or the other. And then it can go through C and E to the output or D to the output. For the pull-down network, starting from ground, if you can go to A and B to the output, if both of these are ones, then these will they'll close the transistors. Same thing. If D is 1, and it's either C or E, have to be 1 in order to create a path to the output. And so that's part 2. And then part 3 is taking these path diagrams and actually creating the circuit. So let me zoom in on both the stick diagram and the path diagrams, if it'll actually let me. That's good enough. Okay, so for the pull-up network, we have our decision. It either has to go through A or B. So we start out from VDD. It either can go through A to this node, like so, or it can go through B to this node, like so. Does that make sense so far? So now we're at this node. We have to get here. There's no short or path that won't allow it to go through. In this case, if it can go through just D, then what happens is it can just go like that to the output. Or we circumvent D, C, and E. Circumvent D around C and E, and then it has to go through transistor E, and it has to go through transistor C to the output. So in that case, if we had B, C, and E, it would look like that. Or if we had A and D, it would look like this. And that allows us to get the logic 1 on the output. So what I've just drawn here is that you put a 0 on A, 0 on D to the output from that diagram, and that's where it looks in the circuit. Now scrolling up here to the pull-up network, that represents we've put A here and going through D to the output. See how these all tie together? So now you're running the different levels of abstraction. Now for the pull-down network, it has to start out, it can go in multiple directions. So here we have multiple outputs coming from ground. So here it can just go through A and B, right? So here it's just going through A, through B to the output. Does that make sense? Likewise, we have to make a decision here on C or E, right? So here C or E. Here it's going through E and not C, and then it has to go through D to the output. And what I've just represented here is it's gone through E and through D to the output. And then finally, what we have here is we have it going through C, doesn't go through E, through D to the output. And I have done this here. And so D and C, if we go back to the original, is actually going through that. Yes.
So as for the pull-up network, do we need an inverter for each input?
You need. What do you mean an inverter?
Like since it's a PMOS.
Oh, okay. So PMOS, the not. Okay, so let me stress that that's not an inverter. This is just the logic diagram. That's not an inverter. Going back, I'm glad you asked that question, so I want to clarify I'll go all the way back. I know, by the way, I'm sorry, I know some of you, this drives me crazy when I do this. PMOS and NMOS, so these are the same. So that one just represents gate source drain, and the circle on there goes to the supply voltage. That just implies it'll activate logic 0, whereas a logic 1 is just NMOS. So NMOS here, that's the input. So logic 1 will allow values from ground to flow through. So, yeah. Any other questions before I continue? All right, so I want to go very briefly into what hardware description languages. We will be covering HTML in a lot more detail than in the next in the 6 iOS courses going forward. Did anybody just know Alex and Allie took my 385 class last semester, so you guys got to know everything you ever wanted to know about Verilog. So the hardware description language is basically using a language in order to properly represent the physical layer. So with code, you're actually you're compiling it down and then you're running it through a computer architecture, right? You're doing this in an arithmetic. You get the values out of an instruction memory, you put them into a arithmetic logic unit or some other get the values from the registers, and you do calculations, or you do a branch or a jump or anything like that based on the code you write. The code you write for hardware description language is actually representing the physical layer, and then from that representation you can take it into a synthesis tool. And for those of you who are taking or have taken 386, you can put it onto a board in order to run it and be able to do different things on the board. Or what you will learn in this class is you can take it in and you can actually design it to a specific technology file. And so the 3 important concepts in hardware description languages are behavioral modeling, structural modeling, and physical modeling. So behavioral modeling is defined here as the explicit definition of the mathematical relationship between input and output with no implementation information. So that can be wire Y equals A and B. So what that means is I say that I want an AND gate there, and I will leave it up to the synthesis tool to determine what AND gate I need and where to place it. Does that make sense? Second one, structural modeling, implicit definition of I/O relationship through a particular structure using interconnection of components. So you can be either connecting AND gates, OR gates, transistors in order to build a full adder and actually have the connection going through from the input to the output. And so the physical modeling is kind of what we're tying in now in the physical space. So you have a layout of the transistor, and you can put a different number of different cells together, and you actually lay it out in the pad frame in order to put it through the lithographical process. I always get that word wrong. And actually lay it out precisely how you want it to. And there's different challenges with each one. Really, really hard, requires a lot of time. Really relatively easy, doesn't require much time, but also you can't control the size. You're dependent upon the synthesis tool, so you can get a lot of size blow. And so structural modeling tends to be in the middle. And so in that CMOS class that I taught last year, we went into more detail than they probably ever wanted to go into how it interconnects wires, the whole 9 yards. We started 3 minutes early, so I'll dismiss you 3 minutes early. But what I want to do here is we'll end with 1.14, and that should be, no, we'll start at 1.14 next week, because I really want to go over that quite a bit. So we'll end at 1.13. Undergrads, find a partner, email me who your partner is. Grad students, find an IEEE transactions journal paper on low power design or synthesis. And if does anybody have any questions? All right, then in that case, you're all dismissed. Have a good weekend.